Real-time global illumination decomposition of videos. Today we'll be discussing a state-of-the-art computational photography technique presented at SIGGRAPH 2021 by Meka and colleagues. This technique enables real-time video editing with realistic light reflections using intrinsic images. To properly discuss how this paper advances the field, though, we'll first need to explain a few key concepts. We'll start with chromaticity and intrinsic images. Light intensity can change how colors look and make it hard to compare colors accurately. Chromaticity is a way around that, where we try to remove illumination from the equation. By dividing an image by its intensity, we are left with an expression of color mostly unaffected by lighting. Occlusion effects tend to still be visible, where corners appear dark due to limitations in camera sensitivity. These areas of low light intensity in the denominator lead to poor results. Clustering techniques can be used to improve the output and remove imperfections caused by occlusion. The term intrinsic images refers to the idea that any image can be broken down into components. In our case, images are separated into reflectance and illumination layers. The reflectance layer, as its name suggests, carries the information on how light is reflected in the scene. This layer is often simplified by the assumption that all surfaces will be matte and reflected light will be diffused. This removes more complex reflections and reduces the information in this layer to the color of reflected light. At that point, chromaticity becomes a convenient approximation of reflectance. The illumination layer, on the other hand, carries the information related to lighting in the image. It shows the color and intensity of light hitting each part of the scene. That information also expresses the shape of objects through highlights and shadows. Here, a common simplifying assumption is that the scene is globally lit by white light. Actually separating these layers requires solving a complex series of math problems, which we'll discuss later. The important takeaway here is that these two layers contain all the information of the original image. Separating them allows you to edit surfaces and lighting independent of each other, after which you can easily recombine them to produce a realistic scene. Since changing surface reflectance won't require redrawing lighting or shadows, realism becomes far easier to maintain while editing. Methods that use intrinsic images for editing have been around for a while. In 2011, Robert Carroll and colleagues published a paper titled Illumination Decomposition for Material Recoloring with Consistent Interreflections. Their state-of-the-art method was able to edit images with realistic lighting and color spills. Though visually impressive, it was relatively slow, and a single 250 by 250 pixel square image would take approximately 3 minutes to be decomposed. In 2014, Genzi Yi and colleagues published their paper Intrinsic Video and Applications. Using different techniques, they produced intrinsic images for video editing. While their method didn't handle color spills, it was much faster than previous methods. Their half-megapixel video took about 60 seconds per frame to decompose. Later in 2014, Bonneel and colleagues published their paper, Interactive Intrinsic Video Editing. Building on the work of previous papers, they improved the speed further and used user input to overcome certain limitations. Their half-megapixel video took about half a second per frame to decompose. In 2016, Meka and colleagues, the authors of this paper, published Live Intrinsic Video. Once again building on previous methods, they improved decomposition speeds and were able to finally reach real time. Their half-megapixel video took about 33 milliseconds per frame to decompose, and this increased speed, as well as changes to their algorithm, meant that their method could process a live video stream at 30 frames per second. This paper improves speed yet again, which allows them to introduce interreflections or color spills while maintaining 30 frames per second. Their method is as follows. Using the first frame, they find a set of base colors using clustered chromaticity. User input can be used to identify regions that are misclustered. Then, for each frame, they decompose the image into intrinsic image layers. These layers include the reflectance, direct or white illumination, and additional illumination layers for each of the base colors. During the decomposition, each frame's chromaticity is used to facilitate finding the reflectance. Finally, they use each decomposed frame to refine the base colors and keep subsequent illumination layers sparse. This is all much easier said than done, so let's get into the math. We'll be dealing with linear algebra, so it's important to remember two things. Sparse is good and dense is bad. Sparse means that the matrix is mostly zeros and less demanding to solve in terms of both memory and processing power. Dense is bad for the same reasons that sparse is good. Image decomposition problems are under-constrained. This means that there are less equations than unknowns, and that there are either no solutions or infinitely many. Instead of being able to solve for a correct solution, we have to create an optimization problem to find the best solution available. This paper sets up their problem using a method called energy minimization. In it, an energy value, or cost, is assigned to each considered solution. The lowest cost solution is chosen as the best option. Costs are assigned using multiple metrics. Each metric can add a penalty, or increase the cost, if a solution disagrees with it. Most of these metrics are referred to as priors and compare each solution with some prior knowledge of what a good result should look like. The first metric is a data fidelity term. It ensures that a good decomposition can rebuild the input image. It compares a solution's rebuilt image with the input image and assigns a penalty if they don't match. There are three priors which influence the reflectance solution during decomposition. The clustering prior ensures that the reflectance solution stays similar to the clustered chromaticity of each frame. The sparsity prior assumes that images contain a small set of objects and that the reflectance layer won't have many color edges. This produces a simple reflectance layer that can be expressed as a sparse matrix. Finally, the spatiotemporal consistency prior makes sure that the solutions look consistent across frames of the video. Pixels are compared against random neighbors in adjacent frames to ensure that changes are gradual. There are four priors which influence the illumination solution during decomposition. The soft Retinex weighted monochromaticity prior assumes that interreflections are present near reflectance edges. It expects that we see strong color spills next to sharp color changes in the reflectance. The sparsity prior assumes that pixels should not be affected by many illumination color layers. Excluding direct light sources, it is assumed that lighting for a pixel in the scene should only be affected by nearby objects. In other words, color spills are not expected to travel far. The spatial smoothness prior assumes that changes in the illumination layer are smooth and consistent. And the non-negativity of light transport prior assumes that, since light adds brightness, the illumination cannot be negative. A set of base colors is identified from the video's first frame's clustered chromaticity. Each frame it is updated using a data fidelity term to make sure the decomposition still matches the input. Additionally, updates are limited in size and variation from the chromaticity to prevent flickering due to large updates between frames. You may have noticed that while the reflectance and illumination layers had sparsity priors, the base color updates did not. The base color updates are dense, but are also much smaller than the intrinsic image layers. If solved together, the small dense portion of the matrix would make finding a solution take an incredibly long time. Instead, this method separates the large sparse matrix from the small dense part and solves them separately. Solving the overall problem by alternating between the two submatrices simplifies the problem enough to run on common GPUs. The results speak for themselves.